Hello everyone. So today we'll start with the last topic of pre-stressed concrete, that is analysis of pre-stressed concrete sections. So far we have seen the basic theory of pre-stressed concrete, and then we have seen losses and numericals on losses also we have done. So this is the last part of this module, that is pre-stressed concrete, analysis of pre-stressed concrete sections. So let us start with this topic. So what do you mean by analysis of pre-stressed concrete section? So basically in the analysis, we are going to find out the resultant stress distribution diagram for that particular member. So that is nothing but your analysis. So we have basically three methods to do this. So we have stress method, and then we have pressure line method, and then we have load balancing method. So in this lecture I will discuss about the first method, that is the stress method. So first let us try to understand the various loading stages. So what is transfer stage? So in this stage, stresses are calculated considering the effect of pre-stressing force and self weight. So I hope you understood by this that transfer stage is nothing but the stage in which external loading is not considered. So before applying the external loading, the stage of pre-stressing alone is called as your transfer stage. So generally we have tensile stresses at the top and compressive stresses at the bottom in transfer stage. So when pre-stress is applied to the section or the member, so the bottom fibers are in compression and the top fibers are in tension. So hence at the top you will see tensile stresses in transfer stage, and at the bottom there will be compressive stresses in transfer stage. So the next is service stage or working stage. It is also called as working stage. So in this stage, stresses are developed considering the effect of pre-stressing force, self weight and external loads. So service stage is nothing but when your external load is also considered, that stage is nothing but your service or working stage. So one note I've written over here, that if percentage losses are given, the pre-stressing force to be considered should be after deducting the losses. So this we will see while we solve the problems. So now let us understand how to find out the resultant stress of a particular section. So here you can see that. So let us consider a pre-stressed concrete beam subjected to external loading, and let P be the pre-stressing force supplied by the tendon as shown in the figure. So here you can see that the pre-stressing force is applied to the tendon, and the external load I have shown in the longitudinal section. So now you can see in the cross section that B is the width of the section and D is the overall depth. So at this stage, these are the stress diagram. So first we have this direct stress due to pre-stressing force. So direct stress is given by P upon A. So this is compressive stress, so hence it is taken as positive. So remember one thing, compressive stresses are taken as positive and tensile stresses are taken as negative. So next you have, due to the external loading, you have bending stresses. So bending stresses, so what happens when due to external load your top fibers are in compression and your bottom fibers will be in tension. So that is the reason at the top you can see that it is plus and at the bottom it is minus. So your resultant stress distribution diagram is nothing but the summation at the top and bottom. So at the top the summation is P by A plus M by Z, and at the bottom it is P by A minus M by Z. Hope it is clear. So now next we will see, this was the case for a concentric tendon. Concentric tendon means it is at the center of the section. So now we will see what will be the resultant stress diagram when you have an eccentric tendon. So let us see for the both the stages, that is transfer stage and service stage. So transfer stage is nothing, as I've mentioned previously, that it is pre-stress plus self weight. So only your pre-stress is considered and self-weight is considered, not the external loading. So here you can see the longitudinal section, and the tendons are provided at an eccentricity E from the neutral axis. So now for this we will see the resultant stress diagram. So this is a cross section. You can see B is the width of the section, D is the overall depth. So direct stress again is given by P by A, and now due to this eccentricity we have stress due to eccentricity also. So stress due to eccentricity is taken as PE by Z. So due to this eccentricity, the stresses which are developed are nothing but at the bottom they are compressive and at the top it is tensile. And the next is the stresses due to loading. So the stresses due to loading is nothing but the bending stresses. So what happens when the external loading is due to self weight, what happens, the section tries to bend, so the top fibers will be in compression and the bottom fibers will be in tension. So hence at the top you can see positive and at the bottom it is negative. So the resultant stress distribution diagram will be something like this. At the top it is the summation of all these P by A. So since this is negative, so minus PE by Z plus mg by Z, where mg is the moment due to self weight. So similarly at the bottom it is P by A plus PE by Z minus mg by Z. I hope this is clear. So next is the service stage. So service stage is nothing but when your pre-stress, self-weight as well as the live load is considered, that is your service stage. So now here we can see the direct stress will remain the same, stress due to eccentricity, and in bending stresses you will have dead load bending moment as well as live load bending moment, that is mg by Z, and mq is your live load bending moment. So for this the resultant stress at the top I will denote it as F top. So it is given by the summation of all the stresses at the top, that is P by A minus PE by Z plus mg by Z plus mq by Z. So similarly resultant stress at the bottom will become P by A plus PE by Z minus mg by Z minus mq by Z. So this is the basic before we start with the actual problems, to understand the stages, that is transfer stage and service stage, and to understand the resultant stress diagram. So this is what we are going to do in the numerical. We will find out the resultant stress diagram for a particular section. So I hope this is clear to you. So I'll just explain the terms involved in these equations. So where P is nothing but your pre-stressing force, E is the eccentricity of the pre-stressing force from the neutral axis, and mg is the bending moment due to dead load, mq is the bending moment due to live load, and m is your total bending moment due to loads. And A is the cross-sectional area of the concrete member, I is the moment of inertia, ZT and ZB, these are the section modulus at the top and bottom fibers respectively. Similarly, YT and YB are the centroidal distance from the top and the bottom fibers, and RS is nothing but your resultant stress. So now with this knowledge we can actually proceed to solve the problems. So let us see the first problem. Okay, so I'll just read out the question. A rectangular concrete beam 100 mm wide and 250 mm deep, spanning over 8 meters, is pre-stressed by a straight cable carrying an effective pre-stressing force of 250 kN located at an eccentricity of 40 mm. Live load is 1.2 kN per meter. So calculate the resultant stress distribution for the center of the span cross section of the beam, assuming density of concrete as 24 kN per meter cube. And the second part is to find the magnitude of the pre-stressing force with eccentricity 40 mm, which can balance the stresses due to the dead load and the live load at the soffit of the center span section. Okay, so let us just understand the question, what is given and what we have to find out. So basically we have to find out the resultant stress distribution, and the second part is to find out the magnitude of the pre-stressing force. So before that, let us see what is given in the question. So the given data is the section dimension is given, that is B is given and the overall depth is given. and the span is given as 8 meters. Your pre-stressing force is 250 kilonewton. Your eccentricity is 40 mm. Live load is 1.2 kilonewton per meter, and density is 24. And what we have to find? We have to find basically F top and F bottom in the first case. In the second case is to find the value of the pre-stressing force when eccentricity is 40. So remember these words, the keywords which are given in the question. I'll just explain you. So to balance the stresses due to the dead load and live load means at the soffit means bottom, at the center span sections. To balance means your F bottom is 0. To balance the stresses means your F bottom is 0. So in that condition you have to find out your pre-stressing force. So that was the hint of the problem. So now let us go for the solution. So I have drawn the cross section and the longitudinal section for you. So you can see all the details in the cross section, width and depth and eccentricity. And the longitudinal section, the tendon is at an eccentricity of 40 mm and the live load is 1.2 kilonewton per meter. So the first step while solving this problem is nothing but to find out your section properties. So this we have already done in losses also. So it's always better to solve your problem in steps so that you understand it. So we'll find out the section properties. So basically in section properties we will find out the area, moment of inertia, your y and your section modulus. So A is nothing but 100 into 250, your I is BD cube by 12 and your y is d by 2, total depth by 2, and z is nothing but I by y. So I hope these values you can find out easily. So we'll just proceed to the second step. Your second step is nothing but to find out the loads and moments. So first we'll find out the dead load. So total load is nothing but your dead load and live load. So it's the addition of your dead load and live load. So dead load of the section is nothing but your section dimensions into the density of concrete. So density is already given in the question as 24. So your section dimensions is 100 mm by 250 mm. So plus the live load is also given to you, that is 1.2. So your total load becomes 1.8 kilonewton per meter. So since you got the total load, you can find out the bending moment. It's a simply supported beam. So the bending moment is given by WL square by 8. So it's 14.4 kilonewton meter. Now the next step is to find out the resultant stress. So the first step is to find out the section properties, then loads and moments, and then resultant stress. So the resultant stress is given by F top is equal to P by A minus PE by Z plus M by Z. So this we have already seen in the theory part. So P, the value of P you already know, it is given in the question. 250 area you can find, you have already found out. E is known to you, Z you have already found out, M, total M you have found out, and Z you know. So your F top is 14.23. So if the value is positive, that means it is compressive stress. And similarly we found out F bottom comes out to be 5.77. So again it's positive, that means it is compressive stress. So we have got the first part of the question to find out F top and F bottom, that is stresses at the top and stresses at the bottom. So now the second part is to find out P when eccentricity is 40. So as I just mentioned you, to balance the stresses. So this is the keyword to understand. So if P is the pre-stressing force required to balance the stresses at the soffit means bottom of the beam, then your F bottom is 0. So that is the condition given to you to find out the pre-stressing force. So using that condition we know what is F bottom, P by A plus P by Z minus M by Z equal to 0. So the unknown is P and others, everything is known to you. So you'll get the value of P, that is 176.52 kilonewton. So this was the problem on your first method, that is your stress method, to find out the resultant stresses. So I hope you understood this lecture and the problem. So in the next lecture I will solve some more problems on this method and also the other two methods. Thank you.